Education. Education, baby. Come on. Education has no end.
Good morning. Our today's lesson is on the metallic bond. Welcome. In a metallic structure, the atoms are arranged like potatoes in a debe. I hope you can picture out how potatoes are in a debe. The delocalized electrons are able to move freely in the metal lattice. So, in that debe, which we are taking as a symbol for the atoms being represented by the potatoes, we have delocalized electrons that are able to move freely on the metallic lattice. The nuclei appear to be immersed in a sea of mobile electrons. Now, the nuclei are the positive ions. Because the valency electrons are delocalized, then the nuclei now, which is the positive ion, appear to be immersed in a sea of mobile electrons. This now constitutes a mutual attraction between the delocalized electrons and the positive nuclei. So here there is an attraction between the positive nucleus and the delocalized electrons. And the forces of attraction are called electrostatic forces because they are between opposite charges and they lead to a strong metallic bond. The sea of electrons, when we say a sea of electrons is so many electrons, bonds the positive nucleus. They form a bond with the positive nucleus tightly into the lattice. And this explains why metals have a high melting point. Since strong forces of attraction exist even in the liquid phase, metals tend to have a wide range of temperatures over which they remain liquids. Now here is a situation whereby you melt a metal. So it can remain in the liquid phase over a range of temperatures. Now look at this structure of magnesium metal. You see what we are calling the positive nuclei is when the valency electrons are released into the metallic lattice and the ions, positive ions, remain positive. We are calling them the nuclei. So there is now an attraction between the magnesium ions and the sea of electrons. Because these electrons you are seeing, they are not stationed in one place. They are able to move within the metallic lattice freely. So that attraction between the positive centers, or we call them the nuclei, and the sea of electrons is so tight that it is not easily broken and it constitutes the metallic bond. Then we have the metallic structure of sodium also. We know sodium belongs to group 1 with one valency electron. Now you notice that the valency electron is delocalized. It is delocalized, it is not in the nucleus. And the positive centers of the nuclei are attracted by the sea of electrons, which is created by the delocalized electrons in the sodium metal, which constitute the metallic bond. The attraction between the positive nuclei and the sea of electrons constitutes the strong forces of attraction, which is the metallic bond, and it is a very strong bond. Properties of giant metallic structures. Now earlier on we learned that the metallic bond will form giant metallic structures. Those are the kind of structures which are created by structures which are bonded by the metallic bond. One of the properties of giant metallic structures is that they have high boiling point and melting points due to strong metallic bonds. It's very hard to melt a metal. You require a lot of heat, not normal heat. maybe heat from a furnace or something. Yeah, the reason is because the metallic bond is a very strong bond. So they are also good conductors of heat and electricity in both solid and molten state. This is due to the presence of the delocalized electrons. So we have seen on the structures that in all metals, there are delocalized electrons. So those delocalized electrons will exist in the solid state and also in the molten state. They are the ones which make metals good conductors of heat and electricity. They are insoluble in water. That is the direct explanatory. They are shiny. Metals are shiny when they are, when they are polished. They become shiny. They are malleable and ductile. Malleability means the ability to be hammered into sheets, and ductile means the ability to be drawn into wires. So let's note that the strength of a metallic bond increases with the increase in the number of delocalized electrons and due to decrease in atomic radius. That is why melting point and boiling point decreases down the group in alkali metals and increases across the period 3 from sodium to aluminium. So note those two factors which constitute the strength of a metallic bond. The number of delocalized electrons. If the delocalized electrons are many, the better the conductor than when they are few. Now, atomic radius. If the atomic radius is tiny, then the packaging will be close to one another. The packaging of the atoms and the bond will be stronger as compared to when the atomic radius is big and there's no that close packing of the atoms in the metal. Electrical conductivity for metals, whether in molten or solid state, is due to the presence of delocalized electrons. So in both cases, it is due to the presence of delocalized electrons. Now let's have a look at some questions about the metallic bond which could be asked in an exam, and we also explore how to answer them. Question number 1. Explain why electrical conductivity of metals decreases with increase in temperature. Why does the electrical conductivity decrease with increase in temperature? I hope you understand the question. Now the answer is, as the temperature increases, the kinetic energy of the electrons increases and they move in a rapid random motion, and the positive senders vibrate, and this interferes with electrical conductivity. Therefore, as the electrons increase their movement, the kinetic energy, the positive senders are also vibrating. So there is confusion. In that confusion, there is the interference with electrical conductivity, and that's why the electrical conductivity decreases. So that's how you answer that question. Question number 2. Explain why the melting point and boiling point increases from sodium to aluminium. Why does the melting point increase from sodium to aluminium? The answer should be, this is because across the period there is a decrease in atomic radius and increase in the number of delocalized electrons from sodium to aluminium. And this increases the strength of the metallic bonding. So number 1, we talk about the decrease in atomic radius across the period. And number 2, we talk about the increase in the number of delocalized electrons from sodium to aluminium. Sodium has 1, so magnesium has 2, aluminium has 3. So aluminium has more delocalized electrons, which make the strength of the metallic bond stronger. And also the atomic radius, which we are saying is a smaller one in aluminium as compared to sodium. Explain why carbon 4 oxide is a gas at room temperature while silicon oxide is a solid at room temperature? Now the answer is carbon 4 oxide has simple molecular structure with weak van der Waals forces, while silicon 4 oxide has giant covalent structure with strong covalent bonds. Question number 4. Compare the melting point of magnesium and sodium metal. The answer should be magnesium has a higher melting point than sodium. This is because magnesium has stronger metallic bonding than in sodium, as it has a smaller atomic radius and more delocalized electrons than sodium. Now let's note the following. The strength of van der Waals forces increases with increase in molecular size. So if the molecule is big, the strength of the van der Waals forces of attraction are bigger as compared to when the molecular size is small. Then something else to note is that the strength of the ionic bond increases with increase in electronegativity and electropositivity of the combining elements. For example, sodium fluoride has a stronger ionic bond than sodium chloride because fluorine is more electronegative than chlorine. So you notice fluorine is more electronegative than chlorine, and that is why sodium fluoride has a stronger ionic bond than sodium chloride. Comparison of structure and bonding. Looking at the table, we have bond type starting with the metallic bond. Metallic bonds form a structure called the giant metallic structure. Their melting and boiling points are high. Their electrical conductivity both in aqueous or molten stroke solid are good. Then solubility in water, a metal is insoluble in water. Then we have the ionic bond. It forms giant ionic structures which have high melting and boiling points. Electrical conductivity is good only in aqueous and molten, but poor in the solid state. Solubility in water of ionic structures is that they are soluble. Then finally we have the covalent bond, which has two types of structures, the giant atomic and simple molecular. The giant atomic structures have a high melting and boiling points. They are poor conductors of electricity both in aqueous or molten and solid states, and they are insoluble in water. Then we have the simple molecular structures which have a low melting and boiling point. Their electrical conductivity is poor both in aqueous stroke molten and solid states. And then the structures are insoluble in water generally, but there are some which are soluble in water. Remember, we said so. Now that marks the end of our lesson. Hope you've been attentive enough and you have been able to understand every point. Let us meet again in the next lesson. Cheers.
Education, baby. Come on, education.